Thanks everybody for coming. It's going to be a fun talk. There are going to be 3 speakers, all from LCO, Yair, Arcavi, Curtis McCully, and Andy Howell. It's really my pleasure to have this happen. So a decade ago, at least, Wayne Rosing showed up to base of operations. We're building a telescopic network here in Santa Barbara. And it's extremely exciting to see that happen and also then yield the science you're going to hear about today. So with no further ado,
Thank you, Lars. Can everyone hear me? Yes. Thank you very much for coming. It's really a pleasure to be able to tell you about this very fun discovery that we had the privilege to be involved in. So this is work done by a lot of people, and as you might see here, there were about 80 papers published on October 16th when this discovery was released, just on the first day. And if you go to this website, kilonovi.org, you'll find our compilation of all these papers that you can sort and look through. So what we're going to tell you is all events that happened on August 17th this year. It was a pretty eventful day in astronomy. It was the first ever gravitational wave detection of 2 neutron stars merging. It was the first ever, it was the closest and best localized gravitational event in general. It was the first ever gamma ray burst associated with gravitational waves, which also made it the first ever event where gravitational waves and electromagnetic radiation were detected from the same source. It was also the first detection of a kilonova, and we will of course explain what all of this means. For those of you who have never heard of this before, don't worry. That also made it the first ever gravitational wave where we could identify the host galaxy of the event and pinpoint its location accurately on the sky. And all of this will become important, as you will see during the talk. These led to discoveries that range from neutron stars' equations of state, so atomic physics, out to cosmology, and in between as well. So let's start at the beginning. When 2 very massive objects merge in the universe, they spiral inwards and emit gravitational waves, which are these distortions in space-time predicted by Einstein 100 years ago. And as you saw in that movie, let me show it again, they spiral inwards, and in the final phases they get closer and closer and faster, and the gravitational waves increase in frequency and amplitude. That is the characteristic signature of an event like this. The way you detect gravitational waves is using a Michelson interferometer. So I'm sure you all know what this is. The basic idea is that you can measure very accurate changes in distance of one arm of the interferometer relative to the other. That is a very exaggerated demonstration of what would happen if a gravitational wave passes through the interferometer. So as you saw, the waves get higher frequency and higher amplitude, and that is the signature you're looking for, and that of course causes a interference pattern between the different arms of the interferometer that you can detect. In reality, these changes are incredibly minute. The relative change between the length of the arm and how much it gets distorted by the gravitational wave is 10 to the minus 21. So they're measuring a 21 order of magnitude effect. Which is why the interferometers have to be very big. So these are the actual interferometers that make up the LIGO Observatory, one in Hanford, Washington, and one in Livingston, Louisiana. That's essentially what they are, just giant Michelson interferometers, very sensitive. The biggest challenge, of course, being able to remove all contaminants, noise, and vibrations. So you must have heard these 2 detectors detected the first ever gravitational wave in 2015. That was from the merging of 2 black holes. It made a lot of news, justifiably so, and since then several other black hole merger pairs have been detected at LIGO. But what happened in August was different because that was the merger of 2 neutron stars, not 2 black holes. Neutron stars are very dense cores left over of massive stars after they explode. It's pretty much the densest thing we know that's not a black hole. The crucial difference being when they merge, and this is a simulation of 2 merging neutron stars, it's a messy process. Material gets flung out. You can see very different types of material being flying out in the equatorial regions. There's this disk that forms around the newly merged object. But basically, the difference between black hole mergers mainly is that material here can escape. And so light can escape as well. So unlike black hole mergers where we only have the LIGO detection and nothing else, In neutron stars merger, the expectation was here will we be able to see light and gravitational waves from the same event because material can escape. So what kind of light do we expect to see? There are two main emission sources we expect to happen. One is called a short gamma ray burst, and Curtis is going to tell you about that right after me. I'm going to focus on the other one, which is called a kilonova. So all that material that gets ejected, because it came from the neutron star, is very neutron rich. And under those conditions, a very rapidly moving, high temperature, neutron rich material, you can get nucleosynthesis in a process called the R process, so rapid nucleosynthesis, which means that neutrons get absorbed into nuclei before they have a chance to beta decay. This happens so fast that you can get neutron-rich nuclei and this way form the heavy elements. So this is the main candidate for where the heavy elements are formed. You need our process to happen. It does not happen in supernovae, or at least not at the right quantities. And so neutron stars mergers were looked at as the source of our process elements because that's where you have the conditions to do this type of nucleosynthesis. You need neutron-rich material that can do fusion. And what happens when it does fusion initially to unstable elements, which then decay into the stable heavy elements. And during this decay, they emit light. And that is the light that was predicted to be seen in a kilonova. So the parameters that were expected were about 10 to the minus 3 to a tenth of a solar mass, moving at a tenth to a third the speed of light. And that combination of parameters makes it that we expect a very fast event that only lasts for a few days before disappearing, and quite luminous, but somewhere in the range of about 1,000 times the luminosity of what is called a nova, which is something completely different, but because it was predicted to be 1,000 times brighter than a nova, it got the name kilonova. That's where it comes from. Andy will show you where these numbers come from later. So the basic physics everyone agreed on, it should be that kind of luminosity scale and that kind of velocity, that kind of evolution time. But the complicated physics was that when you create these heavy elements, you also create a lot of opacity for the light to escape. These elements have a lot of atomic lines, transitions, and it's very hard and complicated to calculate exactly how that's going to affect the material because we don't know exactly what the composition of the different elements will be. So this high uncertainty in composition leads to an uncertainty in how the light will escape. We know about how much energy should escape, but if there are more heavy elements that we call lanthanides, these are elements that are the heavier elements that have a lot of lines that block the light. Instead of having something that rises and declines in a day, it will take longer for the light to escape. It will be fainter and it will be redder. So here you see these are the optical bands versus the infrared energy. This is luminosity as a function of time. I apologize for the units, ignore them. These are terrible astronomy units. Just this is brighter and this is fainter, and this is time. So if you don't have a lot of these elements, it all gets pretty bright in all the bands and declines after a few days. If you do have a lot of these lanthanides that block a lot of the optical light and re-emit it in red, then the optical light becomes much fainter. So, and it was not certain because we don't know what the composition is, how it should look like. And these are just two models. This is the same model with two different parameters, gives you very different predictions. And it gets even worse if you compare it to different models using the same parameters. So here the optical is at a magnitude of 36 compared to a magnitude of 26. Again, here you do have to worry about the units, but I'll let you know just that this 10 magnitude difference between the models is a factor of 10,000 in flux. So this is the kind of uncertainty we were dealing with of what to expect from this. And these are models from this year. Okay, this is not some archaic thing. This is the state of the art. This is where we were. So to me, this is theorists telling us we need data. Okay, we need observations to constrain this. We don't know what's going on. So that's what we did. So here's how we obtained data at Las Cumbres Observatory. So LCO is a very unique observatory run here out of just outside campus. The telescopes are all around the world. There are now 20 telescopes. They're fully robotic. What this allows us to do, as Andy is demonstrating here in this video, is as nighttime sweeps across the globe, we can observe things immediately and continuously. Or more importantly, as daytime sweeps across the globe, we can switch to other telescopes and continue observing something. And this is very critical if what you expect to observe is something fast that evolves quickly and you don't want to miss it. So really the only way to observe something continuously is catch it at different times as night moves across the Earth. And this is the idea of Las Cumbres Observatory and what it was built for. One little snag with this plan, though, is that when a gravitational wave is detected, the region on the sky where it can happen is very unconstrained. So this is a map of the sky. This is an example of a gravitational wave event detected by the two LIGO detectors. The reason you have two, by the way, is so that you can tell kind of a rough direction where it came from by the time difference between the detection in the two detectors. But that is exactly what it gives you, is a direction. So if you want to, what we get from them is it happens somewhere here, and this is the field of view of our cameras to scale. Okay, so we cannot, there's no way we can cover this whole area. It'll take months, and by then the thing has already ended a long time ago. So instead, it's important to remember that mass in the universe is not just equally distributed in the sky. It's in galaxies. So if we know where the galaxies are, that's really only what we need to look at. So this is our strategy, is instead of looking at the whole region, is find the galaxies that are most likely to where this has happened and image those. And the question is, of course, is this feasible? And it is, apparently. Turns out that in a region like this, you only need to look at about 30 galaxies to cover 50% of the mass that's inside a region like this. So there are many, many small galaxies, but they contribute very little mass or probability of the event being in them. So if you just find the 30 most massive galaxies and observe them, which is something we can do in a single night, you've already covered 50% of the probability of where this event happened. And that's what we do. And the other thing that makes it feasible is that we know where the massive galaxies are in the nearby universe, in the region where gravitational waves can be detected. There's a limit to that range, and out to that limit, we know where the massive galaxies are. We don't know where the small ones are. They're faint, and that's harder, but we don't care as long as we focus on the massive ones. So we have this pipeline set up that when LIGO detects a gravitational wave, our listener, which is just a computer that listens for these alerts, receives them, gets a localization, checks which galaxies are there, prioritizes them based on an algorithm where we prefer the more massive ones based on where they are, and other properties I'm not going to get into, but we do get a prioritized list, and then that gets submitted to the telescope, which, as I said, the network is completely robotic. So this can get submitted and observations started without any humans in the loop and within seconds. And so this is also another advantage. It's very fast, and we're likely to have a telescope somewhere in the dark when this happens, whatever time of day it is here. And so the idea is to do this automatically. For the first few cases that we did this, which was this year, we put in a web page where we just see, here's the galaxies you should observe. This list goes down into several more galaxies. We can tweak the parameters if we want to, and there's this big green button that just sends it to the telescope. But the idea in the future is, just let this do it itself, because very early observations are very important. So I just want to say that we're one of many teams that have a plan like this to follow up gravitational waves, but our team is probably the smallest one, and it is led, UCSB led, so by the three of us who you hear from today, and Griffin Hossenzadeh, who's a graduate student here, and Sergei Vasilyev, who's an undergraduate student who did an internship with us. He's at the College of Creative Studies and contributed significantly to this project, plus collaborators from around the world. So this was our plan, and here's what actually happened. So on August 17th, LIGO detected gravitational waves from the merger of a neutron star, and the Fermi gamma ray satellite, which is a detector of gamma rays in space, detected a gamma ray burst 2 seconds later. And actually, they were first to localize it on the sky. This is another version of a map of the sky. And the gamma ray bursts were localized to a very large region on the sky, even larger than I showed you before. But a few hours later, the gravitational wave data was processed, and the localization came there as well. And this included a third detector in Italy called Virgo, which had just come online 2 weeks before. Okay, and that was incredibly important because it contributed to, instead of making this huge sky banana I showed you before that crossed the whole sky, it was a much more localized region. It's still big, it's 30 square degrees, but it's much more manageable. And we probably could not have done this if Virgo was not online to make that region much smaller. So here's a blow up of that. This is the full moon for scale, so you get an idea what 30 square degrees is. Again, the size of our detector, we cannot just cover the whole thing, but we observed about 80 galaxies in there. And on galaxy number 5 on our prioritized list, what our algorithm said was the 5th most likely galaxy to have this source, we found the optical source, which was later we understood was the kilonova. So this is the galaxy. These are stars in our galaxy that are not related, they're just in the foreground. And this new point of light, which was not there and was there then, is the kilonova. This is how we find it. We see this new source of light that was not there before. So this is our discovery image from that day. This is universal time. We were one of 6 groups to have independently decided to image this galaxy within 40 minutes of each other. Everyone who was searching using their own algorithms, their own telescopes, their own prioritization schemes converged on this galaxy within 40 minutes of each other and got very similar images. So that was very reassuring. Now, here's a timeline of events shown. So what this shows is where that galaxy was in the sky as a function of altitude above the horizon. Turns out this position on the sky was not a great favorable position for most telescopes because it was close to the sun, which means it sets very early in the night. So your night starts, you can observe it, but within an hour and a half, it goes below, too low for your telescope to look at. It's too low in the sky. A few hours, a little bit later, it'll be below the horizon. So what happened was the merger happened here. There was a 5-hour delay in getting a localization for different reasons. This is when we got our first discovery image. This was announced by the other groups, and everyone else started following it. But everyone who had, just their telescopes in Chile had to wait 24 hours to see it again the next day. Luckily for us, we have a telescope in Australia, so we could observe it a few hours later, and a telescope in South Africa, we could observe it a few hours later. So we were the only ones that caught it early and were able to observe it every few hours. And this turned out to be very important. So here is the data we collected. This is, again, brightness as a function of time in different bands or different colors. And several things that you can see here. First, this is the first observation in Chile, and that's the second observation in Australia. And between when it was over Chile and it was over Australia, it got brighter. And as far as I know today, we're the only ones who caught this rise, which is going to be very important for constraining models we'll show you later. Right after that, because if you get, this is Chile, Australia, South Africa, Chile. If you only have a telescope at one site, you only get it declining. So this will become very important later. We can compare this data, just so you get a sense. This is the typical stuff we look at, which are supernovae, massive stars exploding, much brighter, much longer time scale. This thing just essentially dropped like a rock in a few days. These units mean that this, for example, the blue light went down by a factor of 10 in one day. We've never seen anything evolve that rapidly before. And what we can do with this data is compare it to models of this emission, which depend on how much mass was ejected, how fast, and this matched what people expected ahead of time and how much of these lanthanides are there. One thing that you can see here is that the blue light is much brighter than the models predict. And so this tells us that this is actually still a topic of debate. This thing was bluer than expected, which means that it had a smaller amount of opacity or lanthanides than was thought, and we're still trying to figure out why this is. We can use more sophisticated models that have a gradient of lanthanides, so different components, which Curtis and Andy will tell you in a second, and get a better fit. And so we can actually, with this data, not just probe how much material was ejected at what velocities, but also start to get an idea of what its structure was in order to explain these different colors. So I'm going to hand off to Curtis now. Yes.
Great. So I'm going to tell you a little bit about the data we collected on this. And I'm going to not just present what we got, but I'm also going to try to present a bigger picture of what the community at large obtained for this object. This is probably the best observed transient in history. There's data from something like 70 observatories. The main paper where all of this was published has 3,600 authors on it, I think. So you think it was hard to coordinate the talk between 3 astronomers, try to coordinate the whole astronomical community to observe this thing. This was also the first time we had a multi-messenger type of transient, so something where it wasn't just the light that we discovered. We discovered gravitational waves, and we did full multi-wavelength coverage of this thing from gamma rays all the way down to the radio. And so we cover the full electromagnetic spectrum. Now, this is a pretty complicated figure from the discovery paper to try and give you a sense of all of the stuff that was going on at the same time. So here's the gravitational wave event. The time is going this way, and it's a logarithmic scale. It's a little hard to read, so I apologize. This is 50 seconds, and then this is in days. And as I said, it's not showing up very well, but this is 1 day, and this is 10 days on that scale. So you have the event, and so this is the LIGO chirp. So as they spiral closer and closer, the amplitude goes up, but so does the frequency. And so you've probably heard that it starts at low frequency and goes up, and this tells you a lot of things that Yair has mentioned. 2 seconds later, you have the gamma ray burst. And then in terms of the EM community and the electromagnetic community, this is when things get really exciting. So every single one of these tick marks is a notice from the GCN network. So these are our messages between the different observing groups. And they started out pretty slow, but you can see very quickly there was an amazing amount of traffic going on about this. So the gamma rays showed up 2 seconds later. The X-rays are absent for quite a while, until about 2 weeks after, which I'll come back to and I'll talk about at the end. UV, and so this is the discovery. So this is the 40 minutes where 6 groups independently observed this same galaxy. So these are the 6 groups. Here's our image that Yair showed you earlier. And after that, we pointed basically every telescope on the planet at this. And so everything from UV, like the Swift satellite, so the UV showed up, or the first detection of UV was a little bit later than the first detection of optical. IR was almost simultaneous. And then radio didn't show up until about 2 weeks after as well. So I'm going to start with talking about the emission we saw from the kilonova component. So this, I'm going to talk more about gamma ray bursts in a second, but this is light from what happened in the nucleosynthesis that produced these heavy elements. Now, again, terrible astronomy units, I apologize. So these are magnitudes. Brighter is up here, fainter is down here. Now, to make this plot readable, we've split the different colors, and so don't worry too much about the shifts between these, but that's just so you can actually see what's going on. The bluest bands in the UV are down here, and then the reddest bands are up here. So the UV peaked and faded very, very quickly. So this is days down here. So the UV light was gone after just 2 or 3 days. Whereas, and then as you go to redder, as you get to IR wavelengths, which is what this is up here, it hung around for 2 or 3 weeks. And so it changed very rapidly from being very blue to very red. This is not what we expect for something that's this bright. It's not, and we're not used to seeing things evolve this quickly. All right. So I'm going to tell you a little bit beyond just images. We're going to talk about spectra for a second. So I know many people are not astronomers, so you may not be used to looking at spectra quite as much as we are. So this is wavelength, and so instead of taking filtered images like you would, like Yair showed, this disperses the light, and then you can measure the light as a function of wavelength. And from this, you can tell something about the composition and things like that. I'll get to that in just a minute. This is our data that we got. So we have data from the SALT telescope, from Las Cumbres, and then 2 spectra from Gemini. We've never seen one of these events before, so we didn't know what to look for. If this had been a supernova, we would have been able to just read off what elements are in the spectrum. So we didn't know which of these features were real, and that was a big challenge in trying to understand this whole thing. One of the things we've noticed is, so say this notch, this feature, could be due to the absorption due to some atomic transition. Well, we also noticed that it's in the host galaxy. And so what we take away from this is that these are smooth intrinsically, which we've never seen a spectrum that's smooth. There are always lines in spectra. And then So typically what we see for, say, a supernova is you see these absorption lines. Now, these absorption lines are produced as material outside the photosphere. So you have some radiating sphere, basically, from inside, and then outside you illuminate this material, and it's absorbed, and it creates these troughs. And this tells you something about both the composition of the material that's outside, and the width and location of this tells you about the velocity. Now, like I said before, kilonova look a little bit different. So everything is blended together. And one of the things we can take from this is that the velocities are very high. So a normal supernova, for example, might have an ejective velocity of 10,000 kilometers per second. These have ejective velocities more like 30% the speed of light, so 100,000 kilometers. So an order of magnitude different. And so this is something we can constrain by having spectra as we go beyond just images. Now, these are similar models to what Yair showed you before for the light curves, but now compared to the spectra. Like with what Yair said before, we underpredict the blue side, the small wavelength side for models. And so this is that first model that Yair showed, and it's just there's not enough blue light. The models predicted that this should be much redder than we observe. Now, at late times, which in this case is 3.5 days after the merger, which is, if you work on supernovae, the late time is a year or 2 years. So it's just different orders of magnitude. It's a surprisingly good fit. This line was from a model that was calculated before this event ever happened. Nobody had ever observed a supernova or a kilonova, and because of that, these are just predictions. So to me, this is a huge triumph of theory. We're going to get to why there are still many open questions about this. What we predict from this is that these had very, very high velocities, something like 30% the speed of light. It didn't produce as many heavy elements like the lanthanides that Yair mentioned before, and the ejecta mass was pretty high in terms of what we expected from neutron mergers. The difference between these two lines is how many of the lanthanides did you produce early or in the outer layers. And if most of the outer layers don't produce heavy elements, then you can produce more flux. But there's still a discrepancy here, so it'll be interesting to see how we do that, or how we can resolve that. So if you expand the wavelength coverage into the IR, there's a beautiful movie from Iso and Pion. You can see how this evolves over time. We're at 5 days now, and so we've never seen something that has starts this tremendously blue thing that's now peaks in the IR and then eventually becomes even more red. This is totally unprecedented in terms of astronomical transients and explosive transients as well. All right, switching gears slightly. What about gamma rays? So that's the general picture of the optical and the infrared. Gamma rays are produced much, much earlier. So the way gamma rays are expected to work, and we think they work, is you have some central engine which may or may not require a black hole. It's a big question that's we're interested to see if we can learn from this event. And then you start a shock wave, and these shells end up having an internal shock wave that collide, and then they emit gamma rays. Now, the important thing about this is that radiation is supposed to be very, very strongly beamed at us. If we're not looking right down the barrel of this, we shouldn't see anything. Now, when that shock wave hits the rest of the material around this, whatever is around this, it can produce something called an afterglow. Now, this is important because this is different than the kilonova. The kilonova is light that is produced by the radioactive decay of these R process elements that Yair mentioned. The afterglow is it's emission from the shock wave hitting material around the neutron star merger from the gamma ray burst. Now, this should produce light all the way from gamma rays down to X-rays, visible light, and into radio. Observationally, we break them into two populations. So we have some set of short gamma ray bursts, which they're short. Who'd have thought, right? And these have durations less than 2 seconds typically. And then you have longer duration gamma ray bursts, which form a different population. Now, people have been studying these for many years, and the main things I want you to just take away from this is long gamma ray bursts are typically associated with young massive stars, and short gamma ray bursts are thought to be, or are associated with old stellar populations. So they are candidates for the first neutron star mergers, but we've never been able to confirm that or even test that theory until now. These decay like a power law, so you expect them to disappear very quickly. This is the same kind of thing. You need to be able to get on them very quickly. So one of the things that people have wanted to use Las Cumbres for is to follow follow gamma ray bursts. Now, this emission starts in the gamma rays, and then eventually it gets picked up in the X-rays. This is a log scale in seconds, and so this is only 5 minutes right here. So 5 minutes from gamma ray burst to X-ray emission. So the blue light tends to show up, and the highest energy light tends to show up earliest in terms of gamma ray bursts. And then optical and UV light, which are these pink points over here, shows up a little later. But again, this is 1,000 seconds, so this is something like an hour. And so this is a short burst. Yep. And so the afterglow you expect the X-rays to be the first thing to show up. But that's not what we saw. So this is the actual chirp that the gamma ray burst saw, and it's very simple, less than 2 seconds. It's a pretty standard vanilla-looking short gamma ray burst, except maybe not. When you look at it carefully, this is a normal gamma ray burst, and it's something like 2 orders of magnitude brighter than this gamma ray burst that we detected along with the gravitational wave event was. And so, because this is so close, this is by far the closest gamma ray burst we've been able to confirm, it looks normal, but it's not. And the other piece that's also weird, that hopefully Andy will tell you a little bit about, is that the X-rays didn't show up right away. So the X-rays for short gamma ray bursts are predicted, and for afterglows should be the first emission you see. You should see it before you even see the optical. It's not the case. So this is days since the trigger. Normally, you would see it right here, but there's no detections until 10 days later. And so something different is going on here, and I think Andy will tell you a little bit more about that. And so I'll end with a different picture of that same host galaxy that we showed before. Now, this is the Hubble Space Telescope version. It's a little bit higher resolution than what we can get from the ground. But it's an elliptical galaxy, and it has an old stellar population. And so this falls in line with what we'd expect from a short gamma ray burst. And so we think we're on the right track, but I'll let Andy tell you more about what's left and all this to figure out.
All right. So here's an animation of what we think is going on here, and it'll show the different components that will explain a lot of this. So notice the frequency gets faster and faster. Then these things combine, explode. There's a jet. There's some blue stuff coming out the poles, and then there's a bunch of other stuff coming out other directions. And then the jet hits some interstellar or circumstellar material, slows down, and I don't know, it looks like a fountain in there. But okay, that's not a simulation. That's like an artist's conception to kind of explain the different components. Now we'll get into what those components are. First of all, what were the masses of stars that came together, and were they really neutron stars? Okay, so what they constrain is something called the chirp mass. It's the different components combined in some weird way. That's down here. That's constrained pretty well. But in units that you can understand better, the total mass is 2.74 times the mass of the sun of both components together, plus or minus 0.04 plus 0.04 minus 0.01. So that's constrained very well. That means that the two individual components are constrained to lie along this line, and then it's harder to work out the individual components of each one because there's a degeneracy between the mass ratio and the spin, basically, or what they call the aligned spin components technically. But basically, what that means is the blue here is the low spin case, the red here is the high spin case. All known neutron stars would basically fall into something like a somewhat low spin case, definitely not getting too high. And so that's the favored thing here. So they think for the low spin here, the primary of the mass of one of them was 1.36 to 1.6 solar masses. The other one 1.17 to 1.36 solar masses. Okay, there's other things like radiated energy, viewing angle, and so on, which we'll get to in a second.
Can you define viewing angle since that's always ambiguous?
Yeah, wow. I have it later. I have the exact definition, which I'll show later, but I'll show it a diagram, which I think has it better in a second. So let's get back.
45 degrees, so it doesn't matter.
Yeah, exactly. Yeah, it kind of doesn't matter. But okay. So here are the rough masses of the star and how they fit into the distribution of known neutron star masses. And so they are consistent with that. Now, if you're an astronomer, you might say, well, maybe one of them could also be a white dwarf, but there are good reasons that they aren't white dwarfs. You can tell something about the equation of state of the stuff, for example, which maybe I'll get into if I have time. But notice there's a gap here between neutron stars and black holes. And some of these masses are known from LIGO, Virgo, the bigger ones. But we don't know what happened to the thing when it got together. Does it stay a neutron star? Does it become a black hole? We have some ideas, though. But first, a little bit of how do you get this kilonova? What does it tell you about the physics of the stuff there? First is that you get some expanding cloud of ejecta, that sort of white torus of stuff. That should cool off because it's moving really fast, but it's kept warm by the decay of R process isotopes. And that forms a power law because you've got a bunch of isotopes with half-lives roughly uniformly distributed in log time. And it goes T to the minus alpha, where alpha is 1.3, basically. So that gives you the heating of this stuff, although the overall level is uncertain to about a factor of 5 because of uncertainties in both the composition and even the nuclear data inputs. In fact, when Dan Kaysen was telling about his models of this years ago here at KITP, there was a conference about this. Many different people got up and said, we can't predict the spectra because we don't know what the R process opacities are. But Dan had some model that could give you something rough, and he was able to predict a little bit of the spectral energy distribution. We'll show a comparison to his models in a second here. Okay, then the light curve timescale. The thermal radiation is released when the photon diffusion time matches the elapsed time. So in other words, they're trapped early on, and then as it expands, they can start to get out. And that timescale is given by this, where the more mass you have, the longer the timescale. The more velocity you have, the faster the thing goes, so the lower the time scale. And then the more opacity you have here, the longer the time scale. So you make it more opaque, it's harder for radiation to get out, it takes longer. Same thing with more mass, there's more stuff, it's like a big old blanket. Or if you move faster, you disperse that mass faster. Okay, so that's pretty easy to understand. The luminosity, which is basically the radioactive heating rate at that escape time scale. That's this. Where, again, more mass gives you more luminosity, and then a higher opacity gives you lower luminosity, and a higher velocity gives you higher luminosity. So, bottom line, more ejected mass, brighter, longer kilonova, higher velocity, a brighter, briefer kilonova. Okay, so this is the typical Lars Bilston thing. You know, if he were giving this talk, he'd spend a lot more slides on this, but in one slide, that's the basic physics. And now another important piece of the information is that lanthanides block optical emission, as you've heard, and they are when you make all of this stuff with the R process, this neutron-rich synthesis environment, you can make some lighter stuff and some heavier stuff. Okay, so we got light R process and heavy R process. For the light R process, most of these lines are iron group homologs, and so they have the D shell valence electrons. For the heavy process, they have F shell valence electrons. So 1 to 10% by mass of the lanthanides, the stuff from 58 to 71 in terms of atomic number, and they have the more densely spaced energy levels, and they have orders of magnitude more line transitions, and so they're 100 times more opaque than iron-like elements in the optical. So just a little bit of lanthanides, and you really block out the optical. Okay, so here's predictions from theory. This is a bunch of theorists that got together to write a paper. So Dan Kaysen had one set of models. Brian Metzger had a different set of models. Jennifer Barnes works with Dan, and so on. But they, so what they predict is, here's the fraction of lanthanides. I don't know why I'm getting, it's an Amber Alert. Well, I'm not going to figure anything else about this in this talk. Okay, so we've got a low fraction of lanthanides in black and a high fraction in red. Okay, so that if we increase the amount of lanthanides, we get a longer, this is a bolometric light curve, so integrated over all energies. We get a longer light curve, and if it peaks brighter and earlier if we have a low fraction. And then if we go into the ultraviolet, optical, and infrared, a strong peak in the optical if there aren't many lanthanides, but if there are, it blocks out this optical light, and then we get a peak out here in the infrared. This is a spectrum at 4.5 days, a theoretical spectrum. Okay, so you kind of understand what scales these light curves at this point. But the other important point that Curtis alluded to is that the higher velocities smear out the lines. So here's a typical, what we might expect to see in a supernova type spectrum. This is light R process, which basically is what's made in a type 1a supernova. Here would be a spectrum at 2.5 days. If the velocities were very low, we see these absorption lines. If you start increasing the velocity, they get smeared out, and at a third the speed of light, it's just featureless. Okay, and then here's heavy R process synthesis, and now this is going out more into the infrared, and you can still see some bumps if the velocity is not crazy high. Okay, so again, this is theoretical expectations. And now if we put the two together, and you have some of this blue component and some of this red component, early on you get, at 1.5 days, a lot in the blue, a little in the red, but then as time goes on, the blue component fades and the red component comes up. Or over here in the light curve, you get the G bands or the blue bands, these JHK or the red bands. So you should get a big peak in the blue early, and then at later times the infrared should come in. And that is what the different teams saw. So what we're saying is you need a sort of blue component to this ejecta and a red component to the ejecta. If it was just all the synthesized R process stuff, we wouldn't see the blue stuff that we saw early on. And if it was just the blue stuff, we wouldn't see the red stuff that we saw later. So here is a schematic. So we've got our merged thing here and an accretion disk that forms within the first few seconds, and then it's pretty hot, and it actually blows off a big wind that may be a tenth the speed of light or more. But then this tidally disrupted stuff comes off to the sides at something like 20%, 30% the speed of light, comes off in these directions. Then there's maybe a jet created, and here's the opening angle of the jet here, theta j, and then here's the viewing angle over here. So this is something like what the viewing angle actually would be to answer Lars's question. Now, if you were, so for short gamma ray bursts, or any kind of gamma ray burst that's been seen, they're seeing basically down the jet. Okay, and if that's the case, this is where you get this afterglow that Curtis mentioned that is different than a kilonova. Okay, so here would be the blue component, and here's the red component, but it's overwhelmed by this afterglow, which is in black here, for a normal short GRB. But we think, in this case, we saw it off-axis, so we saw underneath the jet for the most part, saw the blue component first, then the red component. And so that's what's happening here, luminosity versus time, the blue component first, then the red component, and then the afterglow later. That's why the X-rays and radio came in like 10 days, 2 weeks afterwards. Okay, now, if we would have seen things this way, we might not have seen the gamma rays because they'd have been shot over this way. I should say that this jet slows down when it hits stuff, spreads out, and then you can see that sort of shocking effect. I mean, this is where you get the radio and X-ray from. And so that's why it took a little longer to see this stuff. Now, if we were looking from this side, we might not see the gamma rays and so on. And we might not even see the blue component because it's shielded by all of this other stuff. So it's possible there's a different kind of kilonova out there that's just the red kilonova component. Okay. So that was a simplified version, taking it a little step farther to try to figure out what was left there. Here's a picture from this Kaysen, Metzger, Barnes, and so on paper. So the blue is the light R process stuff. The red is the heavy R process stuff. The blue is more blue and blue light. Red is the more infrared stuff. The first step is when they're merging, these tidal tails are thrown off. In this picture, 0.2 to 0.3 C, and they're relatively cold. Then as the neutron stars come into contact, the later matter is thrown off, but is squeezed into the polar regions, partially by shock heating here at this interface with the pre-existing tidal stuff. And remember, all this stuff is happening within seconds. And it's shot off in the polar directions here. That's this 0.2 to 0.3 C in this picture flying off. And then a disk wind comes in third, and it's lower about 0.1 C. Okay. Now, if this disk wind if a neutron star is formed, some hot neutron star survives for tens of milliseconds, neutrino irradiation causes weak interaction, and it lowers the neutron fraction and produces a bluer disk wind. But if you create a black hole, that doesn't happen, and you get a bunch of heavier elements there, and it's redder. Okay, and so they argue in this paper that means there was a heavy neutron star that survived for at least a little while until it maybe collapsed into a black hole. Now, if you have a neutron star and black hole, you might only get a tidal disruption happen that's one-sided, and then you would not see this blue thing. And so this is just a prediction. Nobody's seen this yet, so that's something to look for in the future. Okay, now, that's for the jet model and saying we're looking off-axis on this jet. There's another alternative model that's called the cocoon model. And in this model, there may be a jet, but it doesn't break out. And in this case, you get some power law evolution of luminosity, temperature, and photospheric radius, and that's explained by the cooling of the shock-heated material, heated by interaction of the jet and the merger debris. So you get a jet started, and it may not break out, or it may break out, but that heats this cloud of stuff in there. Here's a picture from a simulation. The jet's coming up this way, and it doesn't quite break out, but it heats up a whole bunch of stuff here, and that's called a cocoon. So in this, here's the actual data from, this is a Pyro and Juno Kohlmeier paper, where the late time emission here is our process. That's the process I told you about before, like the typical kilonova, the red kilonova. Okay, but they argue that the early time emission is different than that, and well, we know that anyway, the blue stuff. But they argue that this dashed line fits the data well at early times, and it's well described by just shock cooling of this stuff. So you don't necessarily have to have this off-axis jet here, and in this case, the gamma rays could come from the shock breakout of this stuff. You get some shock into this cocoon and it breaks out, and then that would explain the very lower luminosity gamma rays than what we've seen otherwise. So slightly alternate model. Okay, to constrain that, I mean, you can take spectropolarimetry or just polarimetry and that can tell you how aspherical something is. If there's a lot of electron scattering, the polarization, if something's spherically symmetric, the polarization cancels. If it's asymmetric, you get net polarization. Okay, people did measure a polarization of 0.5 early on, but it's consistent with other stars nearby, and so that's consistent with Milky Way dust causing that polarization along the line of sight, and not intrinsic polarization. So it is consistent with the blue component having zero polarization, and so that would imply a not asymmetric blue component, maybe symmetric, but maybe not. But okay, so that maybe that favors the cocoon model, but it's kind of hard to say because there's a lot of variables, including how much electron scattering matters here. Okay, so now, can we say that our process elements were really made here? Okay, so in the theoretical picture here, remember high velocities make seeing individual absorption lines hard, but it could be possible. So here is a solar composition at some given velocity. I forget which one Dan chose here, so probably something like 0.2 times the speed of light. And neodymium is a particularly important element here. And if you decrease it by a factor of 10 over solar, you can see the lines that you expect to see change. If you set it to 0, they change again. And cerium, which I don't know is what cereal is made of. I mean, I never heard of cerium before. But it's you know, if you multiply it by 10 over solar, you can see you get some different lines here. Okay, so looking at the actual data, the only paper that I'm aware of that attempted to do this was the Stephen Smart's paper, where they took a spectrum here at 1.4 days, and they said, okay, here's the model without those lines, and when you put in this case, cesium and tellurium, you get extra absorption right here. So I remember when we were looking at our data, we got all of this, and then this is the region where the night sky is absorbing, and then we spent an incredible amount of time to say, are these dips real or not? But at least they claim that yes, this is evidence for some of these R process elements, and here it is on a different day, 2.4 days after. So there is evidence that even though it's very hard to see when this stuff is at very high velocity, that maybe you can see some of these synthesized heavy R process elements. So here's a table from Brian Metzger about important parameters. I've already told you about the different masses, but of interest here, the blue part of the ejecta, he says, is about 1/10 to 2/10 of a solar mass. For the red ejecta, something like 4/10 of a solar mass. Okay, and our actual data fits to our both optical, the light curves, and the spectroscopy. We got a few tenths of a solar mass. So, not inconsistent with what Brian got, fitting to his models. Now, the other takeaways are gold. They say it created 100 to 200 times the mass of the sun, mass of the Earth in gold. Okay, so maybe this is where the gold comes from. As I joked in the press conference announcing all of this in Washington, D.C., we split the light up into a rainbow, and we did see the R process elements, so there really is a pot of gold at the end of the rainbow if it's a kilonova rainbow. Okay. The uranium is also like 30 to 60 solar masses. All right. So how many of these things are out there, and how many can we expect to see in the future? It depends on a lot of variables. This is different ways of calculating how many of these things there might be. This is using fast optical transients in the red here, short gamma ray bursts in the yellow, constraints from stellar evolution in blue, galactic pulsars in purple, cosmic nucleosynthesis in green, gravitational waves in black, and here's the rate in terms of 10 to the minus 4 per megaparsec cubed per year, and they kind of agree with each other, so we kind of know. It's something like once every 200 years in a Milky Way-sized galaxy. And here's the O1 was the LIGO run previous. The O2 was the one we just finished, and O3 is the one coming up in about a year or so. So we should see some more of these. In terms of how many might be joint Fermi and LIGO detections, it's something like 0.1 to 1.4 of them, so order of magnitude uncertainty And if they reach their design sensitivity in a few years, it goes even higher. Okay, so these are the R process elements here. The yellow are the ones where we think these things were formed by these merging neutron stars. So given the amount of R process elements created, the ejected mass, and the rates that we know, kilonova can account for all of the R process elements. So there may be some that are created in supernovae, but we don't need them to explain the R process elements. And in fact, some have said maybe there's a problem now, there's too many R process elements. But okay, it's super early days where we don't really know. Okay, getting near the end here. You can also do cosmology. These things are standard sirens. They can tell you the luminosity distance to the source. And when paired with the redshift from the host galaxy, you can get the Hubble constant. So we're on this paper that tries to do this. Here's the inclination here, and here is the Hubble constant. And so those two things are correlated. But once you sum over the angles here, you get the Hubble constant is something like this, where Shoes is Adam Rees's collaboration here. Planck is the Planck mission's determination. You can see they're discrepant a little, but conveniently this falls right in the middle, although that's luck because of the errors. Okay, but 70, plus or minus 10-ish kilometers per second. But that's for one determination. This is independent of all the systematics of everything else. So if you do this, 10 times, 20 times, this is going to be a great way to constrain cosmology. Okay, so to conclude, at least some short gamma ray bursts are associated with neutron star mergers. That's what we expected, but it's amazing to have such astounding confirmation that you really know that they were neutron stars, not like we normally do in astronomy and kind of guess. So the kilonova theory pretty much worked. Given the uncertainties in the atomic data, different possible mass ratios, simplifications of the models, orientation effects, is an incredible agreement with what we expected. The bright blue part of the kilonova emission was pretty much a surprise. So we need a multi-component model to explain the data. So it could be that the if it's spherically symmetric, the outer regions are not very lanthanide rich, but the inner regions are. Or it could be these orientation effects that I showed. And it's possible that a massive neutron star survived for tens of milliseconds before collapsing to a black hole. Maybe it survived even longer. It's hard to say. It depends on what neutron star equation of state is and all kinds of other things. The off-axis jet can explain the late X-rays in radio, but maybe it has problems explaining the polarization data. It's not completely clear. Shock cooling of a cocoon is an alternative. And the era of gravitational wave cosmology is here, and we're in the multi-messenger astronomy era. So our observatory, Las Cumbres Observatory, is well positioned to act quickly on future gravitational wave and neutrino alerts, so combining physicists and astronomers together like we've done here. All right, thank you.
Okay, we're going to take questions. So Doug is going to use this new attempt at the shotgun mic, so don't be scared when he points it at you. So we get the question on the internet. Joe.
Yeah, so I had a question for everybody, which is, it seemed like the primary argument that you were seeing a neutron star merger and not a neutron star black hole merger was just the sizes of the masses of the objects inferred from LIGO relative to the masses of black holes. There was a slide that I think Ayer showed on this. I guess the astrophysics is obviously pretty complicated, but you may have just formed a black hole that's smaller than any black hole that's been seen before from X-ray binaries. So how certain is one that this is not a black hole neutron star merger?
Right. Well, I would just say that, as you saw from theoretical pictures, so we can't actually say, so we can say something about the structure business here, and this is from the LIGO paper of how basically this is this deformability parameter, and it's defined in some weird way. So I just excerpted the paragraph where it says what it means. But basically it means these are different neutron star equations of state. This is getting more compact as you go, and this is like one component and then the other component. So one neutron star, the other. And this is the low spin case, the high spin case. Okay, and these are contours that are like, 90 out here and 50 as you go in. So what you can say is, so you cannot actually use this to distinguish between neutron stars and black holes. So yes, you're right, in that from the gravitational wave data alone, you can't exactly say that they're not black holes, but from the optical emission, that matches exactly what we say with theory. So I would argue.
It could be a low mass black hole and a neutron star. How do we know it's not that? That's the question.
So you're right, as Andy says, from the gravitational wave data you get the masses, right? So it doesn't come with a black hole label, it comes with a mass label, and you need a model to tell you could that be a black hole or a neutron star. But from the kilonova emission, these various components that we see match much better what you expect from a merger of two neutron stars than from a merger of a neutron star and a black hole, where the structure of the ejecta would be very different. As Andy said, it would be asymmetric. In fact, some models even go further and can calculate or claim to say how long the merged object was not a black hole for 100 milliseconds after the merger until it collapsed to a black hole, because that's how much time you need to have this neutrino irradiation that would make the lanthanide poor component that we see in the blue light. So this blue light is hard to explain if one of the components was a black hole, because then the neutron star would just be disrupted into the black hole. Whereas if they were two neutron stars and they merged to a very high mass neutron star that lived for 100 milliseconds, is what you need to make that blue component according to these models. So yeah, this is model dependent, but this matches the merger of two neutron stars in terms of the emission properties we saw in the kilonova much better than a neutron star black hole.
But is that really a strong statement, given that you said that the models were initially differed by possibly 4 orders of magnitude in the brightness?
Yeah, but the neutron star black hole models were very different again. So this matches
this as blue as we saw. You need it to be even more neutron star than what we thought before.
And the original neutron stars were well within what we've observed before for neutron stars.
Yeah, so everything points to that. I agree it's not ironclad, but if somebody could make a model doing it with a black hole, it would be interesting.
Question?
So why did LIGO took 6 hours to send localization to observatory?
Thank you for that question. We asked that as well. It's because, if you might have noticed, if they had done it an hour earlier, we would have received the localization when the galaxy was over South Africa, where we have a telescope, and none of the other groups do. So we would have been the first to have found it. So we really asked LIGO, why did it take 5 hours? And all the previous ones, black hole ones, it was immediate. So what happened here was that one of the detectors, the Louisiana detector, had a glitch right at the second of the strongest chirp signal from the merger. So what happens when there's a glitch like this, it's a really short-lived thing, but they just, they just erase, don't erase, but just, we're not going to look at that part of the detection, right? So initially, they only had the Hanford-Washington detection, which they saw was a very low false alarm rate, very strong signal, and combined with the gamma ray burst, they understood something was going on. And the 5 hours is the time they took them to go into the Louisiana data and try to remove that glitch manually and try to work around it. There's actually a figure in their paper where you see the chirp and the glitch is right on top of it. So it was non-trivial. They did a great job in removing that, and then that's what allowed to get the localization, but that's why it took longer.
And the other piece of that is that the Virgo detector, which we said was so important to being able to triangulate this, didn't detect anything. And actually the fact that it was in a blind spot for Virgo is what made that error, or that region on the sky, so small. And so you have one detection in one detector, a glitch in the other one, and a non-detection in the third.
Yeah, so the initial alert was just Fermi plus Hanford. And so our initial thing was that big, huge area in the sky, which we're like, oh, you can't do anything. Except Yair was we have all our triggers built for the actual localization region. And so instead they sent out something not in the correct format, massive area, and so Yair is just plotting the galaxies versus where, and just by hand building a list. So all of our preparation we had done for years was out the window for the first few hours. And we actually started observing all of that region, and so it actually took us it took us a little longer to find it because we're still processing all of our other data and looking at it from the other region, and then we get this new thing. And the other thing is, when we got this new thing, not everybody in the world thought it was a kilonova at first. We weren't sure for many hours, well, that whole day, if this was another supernova or if this was the kilonova. And so, in fact, we were calling up all of our friends trying to get observing time and whatever, and some people were saying, no, let's not observe that because that's not the real thing. That's too bright. That's a supernova because you didn't have a spectrum yet. And so they wanted to keep tiling the region to look for other things. And boy, were they wrong.
But luckily, with LCO, we were able to do both. We were observing this thing with 9 telescopes that we have in the southern hemisphere. So at the same time, keeping an eye on what we thought might or might not end up being the kilonova with multiple colors, and observing the rest of our 80 galaxies in the list with the other telescopes. So it was really this choreographed dance of telescopes that we were trying to coordinate until we realized that's a kilonova, and we just pointed everything at that. But it does also allow us to say that there was no other event in the other galaxies that could have been. So we covered about 85% of the mass in that error region, and we can say this was the only thing that popped up at that time.
Okay, Phil has a question.
In the lanthanide opacity, how dependent on the ionization state, or is it fully stripped? If it's fully stripped, then I don't see how you'd have any opacity. But can you comment on that?
It's not fully stripped.
Yeah, no, otherwise you would have 0 lines. Yes, I think that is one of the uncertainties. In addition to having many lines, is you need to consistently solve for the ionization state to see which lines are relevant.
Let me ask you a question. So LIGO is down for about a year.
Thank God, yes.
So the question is, optical astronomers are not patient people, and so my expectation is somebody will find something and claim to be a kilonova in the intervening year.
All right, I'm prepared for this. It's not patient people. Yeah. Well, we're also not patient, and we're competing. Yeah, so we're competing with everyone. Is this in my? Let's see here. Where is it? It's in this thing. Okay. So the question is basically, did we miss these in any other survey? Can we find it without LIGO? And the answer is no. So the average number of kilonovae expected in all these different surveys, which survey the whole sky or deep parts of the sky, SASN, SDSS, PS1, SNLS, DES, SMT, is 0.3 to 0.0 to 0.3 kilonovae expected in all of those surveys. And so basically the answer is nobody has a survey good enough to just find these right now. Maybe ZTF.
But because they're so fast and faint, without the gravitational waves telling us here's where to look now, it's very hard to by chance find something.
The next year. I didn't care about this.
Yeah. Well, okay, no. So we actually did this calculation. So first of all, the answer is yes. Definitely people are going to claim that they found it. For sure. But whether they really did find it or not, yes. So in the next year, the Zworyki Transient Facility is the next big survey coming online. And they, depending on their survey strategy, may find one after a few years of operation. Depends on how they operate the survey. In a few years from now, the LSST, the big survey coming online, the Large Synoptic Survey Telescope, should find at least, just by chance, find a few dozen of these per year where it can see at least 2 data points before it fades below its detection limit. And these will be at much higher redshifts that gravitational waves detectors are sensitive for, so they will find them only in the optical without gravitational waves. And they should find maybe 1 a year where they have at least 3 points where you can really start to see something.
And then I was just going to say, short gamma ray bursts have also been thought to be associated with these as well. And so there was a short gamma ray burst that people claimed a kilonova detection in 2013. Now, there's a huge difference in the distance. So this was 130 million light years away. That was at redshift 0.35, which is, I think, 5 billion light years or something like that.
And it looks quite different, and so it's not completely clear how it was a kilonova.
Okay, thank you.